הביאו לי משרות ודברים
עכשיו הוא כאילו בשנים של ההפסקה בעצם.
לא, עכשיו כן, אני חושב שזה לא כל עכשיו. אני הייתי שנה שעברה, לפעמים בגלל שכאילו הוא לומד בזה, תוך כדי
Okay, let's start. You hear me? Okay. Are there other students outside or? אנחנו מתחילים אם יש מישהו Okay. How are you handling exercise 3? Is it okay? Not too long?
Too long.
Of course. Of course it's too long. It's not too long. The next exercise, I'll publish the next exercise this Thursday. What's that?
Will be shorter?
No. Well, yeah, it will be shorter because it's just you'll have just a week for that. Although exercise 3, it's not that long. Those of you, anyone use the skeleton I provided?
Yeah.
Okay, so if you use that, you only have to write 2 lines of code and add 1 wall to the maze. That's all. So basically, you need to spend most of the time going over the material, understanding the algorithm, which you should do anyway, regardless of the exercise, and then spend a few minutes implementing it and running it, and then think about the results. Okay, so I really try to minimize your programming time to the minimum possible. Okay, exercise 4, I'll publish exercise 4 this Thursday. Although exercise 3 is due on Sunday, I know, but you have a little bit over a week for that. Okay, so and I'll try to keep it this way. So the exercises will be published on Thursday, and you have until the next Sunday. So you have 2 weekends to juggle between all your work, and I hope that will help a little bit. Okay? I think you asked that, or someone, I don't remember. But anyway, okay. Any questions about the exercises besides that? Okay. So today we will continue talking about the parameter estimation. So in the last few lectures with Tali, you talked about how to estimate a parameter of a distribution, either in the Bayesian approach, right? You saw a few Bayesian estimators, and you also talked about the maximum likelihood approach, which is not a Bayesian approach. So today we'll review that, and we'll see how to find actual estimators for different distributions. So by the end of the class, if someone throws on you a parametric distribution that you never saw before, you'll be able to, you know what to do then, you'll be able to find estimators, different estimators for this distribution. Okay? So let's start. So as I said, the topic is parameter estimation. Okay? And let's just remind ourselves what are the different estimators that we saw so far in the course. Okay, so let's start with the Bayesian approach. What is a Bayesian estimator? Okay, it's simply an estimator that is optimal in the Bayesian framework. What is optimal in the Bayesian framework? What is the objective that we want to minimize in the Bayesian framework? Well, what do you say? The risk, right? We define the risk, which is the expected value, okay, of the error, or the conditional risk. Okay, so in the Bayesian framework, so the Bayesian estimators, okay, they are simply estimators. Let me denote that by theta base, which is just a general notation for any Bayesian estimator. Okay, what does it mean that it's optimal in the Bayesian framework? It means that it minimizes, it's the arg min over all possible values of theta of the conditional risk, right? Or theta given our observation. Okay, and what is the conditional risk? So this is the arg mean of theta of, we integrate, right, over all possible, arg mean theta hat. Okay, the minimal estimator. Okay, so we integrate over all possible values of theta, of the true value, of the posterior distribution of theta given our observation. And here I assume it's continuous, but it doesn't have to be continuous random variable, times the cos function, theta hat given theta, d theta. Okay, so notice that the Bayesian estimators, they depend on two things, right? They depend on the cost function, and they depend on the posterior distribution. So we need to have some prior over theta in order to have a posterior distribution, right? And different cost functions induce different estimators. Bayesian, all of them are optimal in the Bayesian, in the sense that they minimize the risk for different cost functions. So there are different optimal estimators, depends as a function of the cost function that we choose. So which cost functions did you see so far? Right. So one very popular cost function is the quadratic cost, the square error, right? And what is the estimator in this case? So we call it the L2 estimator, okay, because this is the L2 distance between the two, between theta hat and theta, right? And do you remember what it was? We saw that in the lecture. Okay, so go over the notes again. It's actually it's not complicated to show. I'll write it down, but make sure you understand how to show it afterwards. Okay, so this was the expected value of theta according to the posterior distribution. So according to f theta given xn. Okay, so it's the posterior expectation. So this is a property of the posterior distribution, right? By the way, I write theta hat like this, but you should remember that all of these are actually functions of the sample. Right? So we get a sample, and then we evaluate the posterior. The posterior is a function of the sample as well. Okay, and then once we have the posterior, we can take the expected value. Okay? And if, for example, the posterior distribution has a simple or a form of a known parametric family, such as, I don't know, the normal distribution, then it's easy, okay? We don't have to actually evaluate this expectation. We already know what is the expected value of the normal distribution, and we can use that property. Or if it has if the posterior has any other form that we know already some properties about this distribution, then we can just use them. We don't need to evaluate the expectation all over again. Okay? And we'll see examples of that in class. Okay, what other cost functions did you see? The 0, 1, so in the continuous case, it was 1 minus delta theta hat minus theta, right? And what was the estimator in that case? Exactly. It was the max estimator, the maximum of the posteriori, the mode of the posterior distribution, which was the arg max over all possible values of theta of f theta given xn. Okay, and in the exercise, in the next exercise, you'll see another estimator, okay, which is the L1 estimator. So if we take the cost function to be the absolute value between the two parameters, the L1 distance, then we get that the L1 estimator, do you see it here? Okay. We get that the L1 estimator is the median of the posterior distribution. Okay? It's the median of f theta given xn. Okay, so this we will show in the next exercise. Okay, so as you can see, different cost functions gives us different properties of the posterior distribution, okay, as our estimator. So in order to find the Bayesian estimators, what would be a good thing to do to start with? we usually want to find a posterior. Okay? And then we can take, for example, for the L2 estimator, if you find the posterior, then we take the expectation and we're done. And if we get that the posterior has a known parametric form, then just by finding the posterior, we can use the properties of this parametric distribution and we're done. Okay, we'll see an example in a minute. Okay. The other type of estimator that you saw was the maximum likelihood estimator, right? Which is not Bayesian. Okay, so what is the maximum likelihood estimator? Okay, so this is the maximum likelihood estimator, or sometimes it's called MLE. Okay, so what is the maximum likelihood estimator? This is f theta given xn. Okay, so this is the maximum posterior, and the likelihood is arg max theta of f xn given theta. Okay, and it's not Bayesian. Why is it not Bayesian? Exactly, we don't need any prior for that. Okay, we'll talk. You saw that already in the lecture, but we'll talk about it also later on, about the connection between the maximum likelihood estimator and the max estimator, which are actually very similar. Okay, so in order to find the maximum likelihood estimator, it would usually be easier. Okay, in general, when you want to maximize probabilities, it's often easier to maximize log probabilities. Okay, and since the log is monotonic, the monotonic function, so the maximum likelihood estimator is also the maximum log likelihood estimator. Okay, so we can also do arg max theta of log of f xn given theta, and in most cases that's what you want to do. So if you find, okay, so in many cases, if you are asked to find the maximum likelihood estimator, then you would like to you would usually want to take the log. Okay, so let's see an example of how to find. Okay, so we'll take now an example, a simple example, and we'll find both the maximum likelihood and the Bayesian estimators. Okay, so example. Let's assume that f of xn given theta is a normal distribution with mean theta and variance 1. Okay, let's start with the maximum likelihood estimator, MLE. Okay, so theta hat ML is the arg max over theta of, I'm already taking the log, which would be easier. Okay, everyone remembers how this looked? Okay, this is 1 over square root of 2 pi e to the minus x minus theta squared divided by 2. Okay, because sigma here is 1. Okay, and notice that this is just a constant here. Right? So when we take the log, we just get a constant factor, and we can ignore that for the maximum. It will not change the argmax. Okay? So this is just the argmax of log. Okay, so this is of the log of this, right? Which is minus x minus theta squared. I'm sorry. We get a sample, right? So this is just for a single x, right? But if you get a sample, then we assume it's IID, right? So we need to multiply. So it's the product of I goes from 1 to n of f of xn given theta, okay? And as we said, we can take the log, we can take the log of this, which gives us a sum, right? So it's the arg max over theta of the sum I goes from 1 to n of log of f xi given theta. Okay? Any questions so far? Okay, you already saw these kind of calculations, right? Great. So now we can just substitute this by the log of this, right? So this is arg max theta, sum I goes from 1 to n of minus half xi minus theta square, right, divided by n, that's it, right, minus n over 2 log and 2 pi. Okay, and as I said before, this is just a constant, so we can just ignore that. So we are left with arg max over theta. Yes. We continue here. Okay, I'm continuing here. So we are left with arg max theta of minus half sum I goes from 1 to n of xi minus theta squared. Okay? So how do we find the maximum? Just differentiate with respect to what? Theta, right? And equate to 0. Okay? And how do we know that we'll get the maximum and not the minimum or a saddle point? Because this is a quadratic equation. Okay? So just differentiate, it's very easy, and you'll get that the theta ml is 1 over n, sigma I goes from 1 to n of xi. Okay? And you differentiate, the half goes, and that's what's left. Okay? So this is the ML estimator. Which makes sense, right? Why does it make sense? Right, because theta is the mean, the expected value, and we got that the estimator is just the empirical average, empirical mean. Okay? And what is the expected value of the theta ML? If we take the expectation of this, it's theta, right? Which means that how do we call an estimator that the expected value of this estimator? It's unbiased. Okay? It's also consistent, because consistency means that if you take n to infinity, then it converges in probability to the true parameter. So in this case, it's both consistent and unbiased.
Unbiased, you have to have it at n, don't you?
Yeah, unbiased is stronger.
Oh,
okay.
synthetic.
Okay. So this is unbiased, and of course you saw that the maximum likelihood estimator in general is also consistent. Okay, even if it's biased, and we'll see by the end of the class we'll see an example where the maximum likelihood estimator can be biased, in fact. Okay, even though here it's not. Okay. So next, now that we found the MLE, we want to find the Bayesian estimators. Okay. So how should we start? Find the posterior. Great. So let's find the posterior. So to find the posterior, we need a prior, right? The Bayesian estimator. Okay, so now we found the MLE estimator, right? The maximum likelihood estimator. Now let's find the Bayesian estimators. Okay. So now we want to find the Bayesian estimators. Okay, so we need to assume some prior, right? So let's assume, yes. You still writing? Okay, sure. We need to assume a prior, right, in order to have the posterior. So let's assume a prior that will make our life easy. Okay, so we'll take f theta to be also the prior to be also a normal distribution with, say, mean mu 0, and variance 1. Okay? It will be easy.
Can we just assume any variable one?
So that's almost a philosophical question. In general, if you have, the prior should reflect some knowledge that you have about the world. And we'll see that in a minute when we get the actual estimators. You'll see that the prior induces some inductive bias. Okay? And if you want this bias to be as accurate as possible, or to reflect something that you know about the world. However, in many cases, it's not very clear how to bring this prior, right? Sometimes we don't have enough knowledge. So one popular approach is to select a prior that is mathematically convenient. Okay, and we'll see an example for that. Or even this would be an example of that, but we'll define this more generally in a minute. Okay, so let's start by finding the posterior. So now that we have a prior, we can go ahead and do that. Okay, so the posterior f theta given xn is proportional, and this you saw already, to what? Okay, let's not do proportional on it. It's actually, it equals, okay, we use base rule, and we get that it's f of xn given theta times f of theta divided by f of xn. Okay, but the posterior is a distribution over theta, not over x, right, or xn. And therefore, anything that does not depend on theta, when we consider this as a function of theta, is just a constant with respect to the variable of the distribution, right? So we can just ignore, okay, this is a trick that will, a very useful trick that we'll do a lot, especially in these cases. We'll ignore all the constants, we'll put them aside for a minute, and then at the end we will take care of normalizing the distribution. Okay, because in general, just evaluating f of xn could be complicated, and we don't need to do that. Okay, once we just find the terms that depend on theta, it is much easier to normalize the distribution. Okay, so this is just proportional to this. I'm just ignoring f of xn, and I'm hiding all the constants here in the proportional sign. Okay? Also, we have constants, right? 1 over square root of 2 pi is also a constant. So we'll ignore it for now, and we'll take care of normalizing the distribution at the end. So this is just proportional, okay, to the product of e to the minus I goes from 1 to n, e to the minus xi minus theta to square divided by 2. Okay, this comes from the first term, from the likelihood, times the prior, e to the minus theta minus mu 0 square divided by 2. Okay? This is just equals the exponent, right, of minus 2 minus half sum xi minus theta squared plus theta minus mu squared. Actually, I didn't do anything. Just you can't see. Did you finish writing this part?
Yeah.
Okay. Okay. So basically, from here to here, I didn't do anything. Just if you're multiplying exponents, so it's like summing in the exponent. Yeah. Here are multiplied. This is in the exponent. What is the question? Okay. If you multiply outside of the exponent, it's like summing inside of the exponent. Okay. So this is the only thing I did from here to here. Okay. Now notice that this here is xi squared minus 2xi plus 2xi theta plus theta squared. Okay? So here the first term, sum over xi squared, is also a constant with respect to theta. So we can ignore it for now. Okay? And also here we get that mu0 squared is also a constant with respect to theta, and we can for now ignore it. Okay? So this is just proportional to the exponent, and I'm leaving only the terms that depend on theta. Okay? The exponent of, so here we get n times theta squared, right? Because we have here sum from I to n. And here we get, from here we get 1 theta squared. So we have n plus 1 theta squared, right?
From the equation, isn't it like the prior is just equivalent for an extra measurement?
We will get that, okay? But we're trying to derive it, okay? So you're jumping to the final result. But your intuition is correct. I didn't hear you. I can't hear you.
In the third line from what about
Yes.
the multiplication, the f of theta.
F of
Yes.
this. This.
Yes. It's outside the.
Yeah. Okay? Because here, this is a multiplication of n terms, and this is just. Okay. So let's go back to here. Okay? So we had n plus 1 theta squared. Okay? Minus 2 theta. And from this term, we get here sum of xi. And from here, we get plus mu0. Okay? And again, I'm neglecting all the constants. They're hiding here. Okay? Now let's do just a simple manipulation on this. Okay, so just a simple manipulation. This is exactly the exponent, right, of minus 2 n plus 1 theta squared. I'm just dividing everything by n plus 1. Theta squared plus, minus 2 theta 1 over n plus 1 sum xi plus mu 0. Yeah. Okay? I didn't do anything. I just divided this. I just divided everything by n plus 1. Okay? This and this. The nominator and the denominator. Okay, so what does this remind you of? What kind of distribution is proportional to this distribution? Okay, or let me ask it differently. Okay, when you get something like this, what do you want to do with the denominator? Okay, as we can ignore constants, okay, we can also add constants. Doesn't matter, we'll normalize everything at the end. Okay, so we would like to complete this to the square, right? And then we get that this is proportional, right? Because completing this to the square just it amounts to adding just a constant with respect to theta. So this is proportional to the exponent, right, of minus theta minus 1 over n plus 1 sum xi plus mu 0, all of this to the square, divided by 2 times n plus 1. And now, what is this distribution? It's a normal distribution. Okay, we already know. Okay, so this has the form of an unnormalized normal distribution, and we know what is the normalization factor. Right? So we get that the posterior f of theta given xn is the normal distribution with what is the mean?
1 over n plus
times xi plus mu 0, and what is the variance? 1 over n plus 1. Okay? It should be, yeah, I should have written it this way, right? Because I multiplied the numerator and the denominator by 1 over n plus 1. Okay. Right. Okay, that's cool, right? Because now we know already all the Bayesian estimators, right? What is the L2 estimator? It's the expected value according to the posterior distribution, right? So what is the expected value according to the posterior distribution? Just this term, right? So the L, just 1 over n plus 1, sum xi plus mu 0. Are we done with this? Getting better and shuffling the board, right? So we get that the L2 estimator is simply the expected value, right? What is the map estimator? What is the peak of the normal? Where do you get the peak at the normal distribution? It's the same, right? It's also the map estimator. Okay, and what is the median? In the normal distribution, it turns out, it's not always this case, right? But in the normal distribution, this is also the median. So we get that all three Bayesian estimators are just, okay, so we worked hard to find the posterior distribution, but now we immediately got all the Bayesian estimators from this distribution. Yeah?
What about all the normalization factors we...
Okay, so you know already, because this has, okay, this is all the terms that depend on theta, right? And so we know how to normalize this distribution, because this has the form of an unnormalized normal Gaussian distribution. So tell me, what is the normalization factor? It's just 1 over square root of 2 pi, 1 over n plus 1. Right? So that's the normalization factor. Okay. So this is a useful trick to ignore constants, but you need to be careful to make sure that you know what is the parameter of the distribution and what is constant with respect to this distribution. Okay? What is the variable of the distribution? I'm sorry. Okay. So let's observe a few nice things. Yeah. Equal. What is what equal? Right. Okay. So what is okay? We found that it's a normal distribution with these parameters. Okay. So this is mu and this is sigma squared. Okay. So the L2 estimator is the expected value according to the normal distribution, the posterior. Yes. Okay. So this is why we got this. The map estimator is the peak. Okay. The maximum of the posterior distribution, which is in the Gaussian case, the normal distribution, it's the same. Okay? The maximum is obtained at the expected value. And also the expectation, mu, in the normal distribution is also the median. Okay, so this is a special case where all the estimators are exactly the same. It doesn't have to be this way. Okay, so let's observe a few nice things about this estimator. First of all, as you said, right, that the prior behaves as if we added another sample. Right? Notice that, what was the MLE, the maximum likelihood estimator? I think we still have it here. You have it here? Oh, yeah. We have it here. Right? So this was the maximum likelihood estimator. It was just the empirical mean. Right? Here we get that it's, instead of 1 over n, we get 1 over n plus 1, sum of xi plus another sample. So the estimator behaves as if we added some pseudo, like some dummy sample, xn plus 1, with what value? Mu 0, right? Which is the expected value of theta according to the prior. Okay, so this comes from the prior. Okay? So this, as I think you mentioned before, that the prior added an inductive bias. Okay, so if we have very few samples, but if we don't see any samples at all, we say, okay, the most likely value of theta is mu 0, right? But if we get just a few samples, then we still give some weight to mu 0, right? And what happens when we get a lot of samples? Then the effect of this prior, the effect of mu 0, just decays to 0. So we ignore the prior and we give more weight to the data that we see. And this also makes sense, right? As we get more and more data, we're more confident, right, in our samples, and we tend to trust them more than we trust the prior. Okay? So let's show this a little bit more formally, that this has an inductive bias. So what is the expected value of theta L2 given that the true parameter is theta? Okay? So this is just 1 over n plus 1. This is constant, right? So it's just the expected, okay? So it's the expected value of sum xi plus mu 0. Okay, but this is just a constant, and the expected value of xi is theta. So we get n theta, n times theta plus mu 0. So we get n theta plus mu 0 divided by n plus 1. Okay? So it's biased. Of course it's biased. We use the prior, right? But what happens as n goes to infinity? Right, converges to theta. So it's consistent, which also makes sense, right? The effect of the prior becomes negligible as we get more and more samples. Okay? What else is interesting about this is that the posterior distribution also has a nice form, right? First of all, notice that the variance of the posterior goes to 0, right, as we get more samples. So what can you say about the posterior distribution? What happens to the posterior, not just to the estimator, but to the whole posterior distribution as we get more and more samples? Like that? What do you want? Right, it becomes narrower and narrower, more peaked around around the expectation, okay? But as we get more samples, mu 0 becomes negligible, so it becomes more peaked around the empirical mean, but the empirical mean, as you saw here, also here, converges to the true parameter. So as we get more and more samples, the whole posterior distribution becomes more peaked around the true parameter. Okay, and at the limit, it will be a Delwyn function. Okay, so it's not just the estimator, but the whole posterior distribution. Okay, and another very nice property of the posterior distribution is that we can easily update it. Right? If we get a new sample, we don't need to work to do this whole thing again, right? We don't need to work to normalize the distribution. Okay, we just need to keep n in the sum of all the samples that we saw so far. And if we get now a new sample, the update is additive. Right? We just add xi to the sum, and we update our counter of n, and we immediately have the posterior distribution. Yeah?
Conceptual, but in the non-Bayesian case, we essentially treated the empirical mean as if it was our prior.
No. We don't have prior.
No, but when you added, when you made it kind of the squared form, right, you added.
In the non-Bayesian approach, in the maximum likelihood?
Yes.
Okay.
And eventually what you got is
I'm not sure.
Yeah, maybe
Come to me during the break, and I'll try to ask you again. Okay. Great. So we said that the posterior distribution has a nice form, right? It's easy. If we get more samples, we can easily update the posterior distribution. Moreover, the prior and the posterior has the same parametric form. Okay? So this is a very convenient mathematical property, which we would like our prior to have. Okay? Because if we have this, then everything, our whole calculation is easy. Okay? And the next example that we see is exactly that. So in this case, when we have that the prior and the posterior have the same parametric form, we say that the prior is a conjugate prior, okay, to the parametric family of P of x given theta. Okay, so in this case, we just saw that the normal distribution is conjugate to itself. Okay, so let's write it more precisely. Okay, so when we talk about conjugate priors, okay, so we have the posterior, p theta given xn, and we saw already that it's proportional to p xn given theta, the likelihood, times p theta. Okay, so this is right, this is the prior, and this is the posterior. So we say that the prior, so if this belongs to some parametric family, okay, so we say that this family is conjugate to this parametric family if the prior and the posterior belongs to the same parametric family. Okay, so this may be abstract. So in the normal distribution we had the prior was normal, it was n mu 0 and 1, but we can actually take it to be any sigma 0, okay, and variance. And here we took normal distribution with theta n and 1, but we can actually take here also a different, okay, variance, doesn't matter. And here we got that the posterior, let's stay with our example, okay, so here it was 1, and then we got that the posterior was also normal with 1 over n plus 1 sum xi plus mu 0, right, and 1 over n plus 1. So we just took these parameters of the prior, we just updated for the posterior. As we get more samples, we just update the parameters. Okay? So this family is conjugate to this family. And in our example, the normal is conjugate to itself. And we'll now see another example where there are different distributions. Okay? So that's our next example, and I think we'll start it after the break. Okay? So see you in 15 minutes. למה זה נוח?
אמרת את זה או
אמרתי את זה, אבל אתה יכול להשאיר את המסר. יכול להיות שכאילו אין לך קשר.
נוכחתי בזה, שתהייתי אבדק את זה, כאילו כל בהינתן עוד
אבל זה נוח שהחברה שלך בפסיר שלך נותן לך. אז אתה מייצג את זה וזה שם אותו סט פרמטרים. אתה מאשים את הפרמטרים. אז אתה מציג במיוחד אחד, עכשיו קיבלת אובזרבציה,
גם אפשר לעדכן מה?
אתה לא יכול לעשות את הפרמטרים. אתה לא יכול לעשות את הפרמטרים.
אבל שקרו לנו, באמת, נגיד לי נדע שזה נורמלי וזה לא נורמלי, זה לא יודע, פרסון, בסדר? אז יש לי פרמטרים עברו נורמלי, עברו פרסון, וישבו נגיד
קונג'וגט כאילו תמיד יגדיר סיכון מוח. זה מתקיים תמיד באופן קונג'וגט. אז קונג'וגט זה אקספוננציאלי רק אז זה נוח.
הרבה פעמים זה לא חייב להיות משחק אקספוננציאלי, זה לא אקספוננציאלי, אבל לפחות אקספוננציאלי זה יותר בהתפלגות הנורמלית, זה הכתרת שלו, קודם כל זה למה השתיים זה השתיים זה הרי מגידה והמוכנת שתי מסתירים, אז זה פשוט הפחת. אבל מה, איפה, אבל זה עכשיו תהילה גיוון, אז איפה מתקבל המקסימום? בדיוק. ואיפה המקסימום? אבל זה תכונה שאני חושבת המורה. כן, לא תמיד זה ראשונים, הם רואים משהו מוכר, כאילו, לפעמים זה קצת מאוד מוכרים. אבל במקרה הזה, אגב, אני גם דוגמה שבו one English, we see the example where the math and language is the same. This almost for normal distribution, but in normal distribution varies, right? Because the peak is the same.
Just in terms of, so we moved to this, from this to this, right? And we added, like, new zero after, like, completed it to the, and then instead we'll remember it and then normalize, right?
Right.
We
So
constantly did it, yeah.
From here to here we normalize.
We didn't normalize, we just added a factor, instead we will normalize.
No, here, this is not normalized.
Right.
But this is normalized. We just concluded because we got this form.
No, from this to this is just kind of writing this form in
This is normalized.
Yes.
So this the first sentence by constant sign.
Right. Okay. Let's see. But I'm not clear on the meaning of having the additional dummy variable in the non-Bayesian case. For it to
In
be
the non-Bayesian case, you don't have dummy variable. In the Bayesian case, you have dummy variable. This is Bayesian. This is
when we did, yeah.
the maximum likelihood is not Bayesian.
Yes, no, I know. Maximum likelihood is not Bayesian.
I'm not sure why
You're not sure about this?
I'm not sure why it is experience of theta given theta.
Right.
Why this
So
is
you're absolutely right that biasness is not something that we talk about in the Bayesian. Why? Because in the Bayesian approach, this is already optimal. Right? And of course we have bias. But you can still talk about bias in the observation approach. Right? So what does it mean for you to detect the expected values of this? Overall S, exactly.
So
Given that theta is the few parameters.
Okay, that's me. So all X is coming from a single set of the
Right. So this is like taking
Okay, it's not trivial this.
Okay, so it's equivalent to writing this, but saying the expectation of
Yes.
X of X and
Yeah, or X coming from solution.
yeah, it's the same.
Yeah.
It's two different, two equivalent ways to.
Some
And you said
abuse, I would say.
lots of abuse, but you're mature enough. I expect this. If you have more questions about אתה שאלת אותי על המבחן? כמה סטודנטים יש לכם היה על זה?
לכל מי שנושא למדי, שזה כל שם את זה שוב
לא, מה זה בעיה? זה שבוע ללמוד על המבחן.
לא, 5 ימים.
למה 5 ימים?
כי אנחנו חוזרים ב-31 לילה אנחנו חוזרים. אנחנו צריכים ללמוד מהראשון. המבחן הוא בשביעי. אז 6 ימים. אז חשבנו על זה, זה כאילו יום וחצי זה מבחנים, יום וחצי זה תרגילים, ועוד 3 ימים לעבור על החומר. כאילו, זה נשמע לי...
קודם כל, זה פשוט תרגילים ספק. מבחן משתנים בבוקר, אז יכול להיות רק בצהריים, ויכול להיות בגלל שהוא מוכר, אבל אפשר להתחיל ב2:30, 5:30,
לפעמים נוטים להתארך.
אנחנו נשאר שלא, אני חושבת שלא היה רוצים ארוכים, אני חושבת שזה נכון, לא סטודנטית זה לא לאט,
לא.
אבל לפעמים כאילו, אנחנו מכוון שזה לא יהיה טוב, אבל
ואין טיפול בוקר שלום חרד? כי זה דרשת אולי לשאול?
לא,
לא.
כאילו, לא בבוקר זה מוכן, בערב זה מוכן,
זה כן, לא.
אז טרייד-אוף, זה מבחנות לא עשינו. אז לא אכפת לי להעביר את זה לשני 2:30, זה 2:30 לי, אבל אני חושבת ככה.
כן, זה יום.
אז אם אתה יכול לארגן לשאול, אם יש את הרוב, מה לרוב, אז את כולם, יש פה את כולם.
יש לי לשלוח הודעה לכולם, כאילו, כקבוצה, בפורום או משהו? לא פורום, כי אז צריך להגיע לכולם ולא כולם עכשיו פה. כולם עובר על ה-300. אולי, הייתי יכול לשאול משהו. כאילו, אני יכול לפתוח את רשימה שהיא...
שלח לי מייל, ואולי תפתח את זה באינטרנט, ואני אעלה גוגל דוק או כל משהו ואני
כאילו אומר שהמחיר הוא פעם אותו כאילו משפט מסתבר ואז אתה עניין שגם כשאת נורמלי גם כשהפי מגיע מנורמלי אז העדכון הוא מאוד קל ואפשר לתאר את הכל במסתם פרמטרים כלומר מיועצת ומיועצת פה כי אותו הכל מחזיק רק מיועצת תטא ובינתן גימה פשוט מעדכן את ה-M ו-X וזה לא משנה את ההגדרה של עצמה. ממש טוב, היא לא הגדירה את זה. היא אמרה שכאילו זה ממש מקל על העדכון שאתה מקבל עוד תנועות. היא ככה אומרת.
כאילו זה קונג'וגט עוזר?
זה לא תמיד ככה.
או בהקשר הזה?
קונג'וגט. ואני צריכה לחקור על מקור שזה לא נורמלי, זה לא זה דבר. אני שואל אם זה תמיד קונג'וגט, תמיד זה הפתרון הנוח.
חוזרים, זה כאילו זה פעם אחת משפחה, אני חושב שכאן לעבוד עם זה.
לא יודע, יש פה קטר של שתי סוגריות, ואני לא חושב שכל בוט כאילו שהיא זה, כאילו שתי מסוגות שלנו, אז תקף מביניהם מה עושה לך. משפחה, כאילו משאיר אותה.
כאילו נראה לי עכשיו זה הפרטים, אני צריכה להספיק לעבור על זה, אבל כאילו לפחות לעשות סדר בשתי ההרצאות האחרות של למה עשינו כל דבר ואת ההקשר של הכל.
לראות מה בדיוק הפרמטרים שלה?
אז יש לך, המצב העולם שלך בפרונט אופרטני זה פרמטר תטא, יש לך התפלגות עליו, אתה מנסה לראות בתוך האספציות.
פרמטר של מצב העולם.
זה לא פרמטר, זה מצב העולם. כן, אם היה לנו, אני חושבת שאתה להכיר בזה, יש לנו מצב עולם, אובזרבציה, ויש לנו פה איזושהי פעולה זה היה בשירים בעולם, מה קורה בשיעור? ה-W עומד בסטה, עכשיו יש לנו פי של ו-X בסיטואציה גם מאיזשהו פולישי. ואלפא ברוב המצב זה אותו כמו של פעולה, זה המשמעות הפרקטית זה אלפא תטא. זה מצב מיוחד של פעולה שבה אנחנו, המטרה שלנו שהפעולה תהיה סביב התהליך. כמו שכשרצינו הכרעה במצב העולם, אז הפעולה שלנו הייתה להכריע במצב העולם. הטבע זה איזשהו פרמטר בעולם. גם מבחינתנו זה מצב העולם. זה לא פרמטר אישי. זהו, אבל זה מצב העולם. זה לא פרמטר של ההתפלגות.
אפשר להגיד שלפני זה יש עוד תלמידים שמביאות כל הזמן שמביאות במצב העולם? נגיד, אני יודע שכל העולם הוא בהתפלגות כלשהי? עכשיו, מה בדיוק
אני רוצה להזכיר את זה משהו ידע או איזשהו עמדה של מצב העולם.
אני יודע שזה סתם דוגמה, אני יודע שהעולם הוא נורמלי, שאני חפש את זה, לא יודע.
כן, אני אומר לכם, קטע זה פרמטר. נגיד היום מה שרוצה גובה של גובה ממוצע אוכלוסייה ואיקס דגימות של פגים של משתמשים. כל עוד זה כן, יש לך רעיון שהגובה ממוצע אוכלוסייה מתחלק במטר נורמלי, שיכול להיות מטר 60, מינוס משהו. לא, זה איזושהי שונה. אז הוא צריך לראות אובזרבציה. ואפשרות שזה טוב להרגיש של החיים המתאים. אבל מעדכן את העדת רעי שלך. אבל מעדכן אותו ככה שטובה יותר.
Okay, let's continue. Okay, I want to continue. So just before the break, one second. Please try to be back on time. Okay, please try to be back on time after the break, especially when we went on a break exactly on time, so it's important. Okay, so just before the break, we started to talk about conjugate priors, and we saw that this is actually a very convenient property to have from the prior. There are also other methods of choosing a good prior. Okay, but we'll see another example for this approach. Okay, so the next example is to show, let's show that the gamma distribution is conjugate to the Poisson distribution. Yeah.
Before that, what you said about easy updating is true for all conjugate priors or just specifically for our case?
So it will be easy for conjugate in general, okay? Because basically it tells you that okay, the prior and the posterior belong to the same parametric family. Okay, so we only need to keep the parameters of this family, and then we get more observations. We just update the parameters. Okay, so in principle, it doesn't mean that the update is. It's not the same parameters. Like.
So why do we only need to keep the prior parameter?
No, we don't need to keep okay, this belongs to some. Okay, let's see an example, and maybe it will be more clear. But in general, the prior belongs also to some parametric family, and the parameters of this family we call them sometimes hyperparameters to distinguish them between theta, which is the parameter of this family. Okay, so it might be a little bit confusing. Let's see an example, and it will be more clear. Okay. So let's show that the gamma distribution is conjugate to the Poisson distribution. Yeah. No. No. If this is conjugate to this, it doesn't mean that this is conjugate to this. Okay? Not necessarily. Well. Okay. So.
But conjugate doesn't mean that they come from the same family?
It means that the prior and the posterior belong to the same family, but this is not necessarily. Let's see an example. So this, okay, let's see an example. I think it will be much clearer. Okay, so we'll show that the gamma distribution, so let's assume now that this is gamma, is conjugate to the Poisson distribution. So assume this is Poisson, this is gamma, and in order to show that the gamma distribution is conjugate to the Poisson distribution, what we will have to show? That this belongs to the gamma distribution. Great. So what is the Poisson distribution? Px given theta is theta to the power of x, e to the minus theta, divided by x factorial, and x is a natural number. Okay? It's a discrete distribution. And what is the gamma distribution? F of theta. And let's suppose the gamma distribution has two parameters, alpha and beta. Okay, so it's beta power of alpha divided by the gamma function, which is this is just a normalization factor, times theta to the power of alpha minus 1 times e to the minus beta theta, and this is for theta for non-zero values. Okay, and the parameter of the Poisson distribution is also non-zero. Okay, so this is good. This part is. So these are our priors. This is our parametric family of x, and we would like to show that. Okay, so this is gamma with parameters alpha and beta. Okay, what is the expected value of the gamma distributions? Okay, so the expected value of theta according to the prior is just alpha over beta. Okay. You don't have to remember this, although it's easy to show. Okay, but we can use these facts that we know the gamma distribution already. We know some properties of this distribution. Okay, and the mode of the gamma distribution, if alpha is greater than 1, and let's assume it's greater than 1, it's alpha minus 1 divided by beta. Right, so this is according to the prior, the השכיח, the peak of the distribution. Okay, so we'll use that for the map estimate. Okay, so these are known properties of the gamma distribution. Okay, yeah. Okay, so these are general properties of the gamma distribution. So we have them for the prior. We also have them for the posterior. Okay, but now we just need to find the posterior. Right? So as we did before, f of theta given xn is proportional. Right? I'm doing the same trick I did before. It's proportional to p of xn given theta times f of theta. Right? And now this guy here, okay, is just the Poisson distribution. Okay, and we assume IID samples, okay, as we usually do. So this is just the product of I goes from 1 to n, right? Theta to the minus sum, right? Minus xi, we'll get a sum in a minute, divided by xi factorial, e to the minus theta, right? This whole thing times times the prior, but this is a constant, so I'm ignoring it for now. Okay, so I'm taking only the terms in the prior that depends on theta. Okay, so it's theta to the power of alpha minus 1 times e minus beta theta. Okay, so this is proportional to. This is confusing, probably. Okay? Great. Now this factor here is also constant with respect to theta, so we don't really need that. So this is just proportional to theta to the power of minus sum xi, I goes from 1 to n, times, here we get e to the minus n times theta, okay, because we're multiplying this n times, theta to the power of alpha minus 1, e to the minus beta theta. Okay, let's just reorganize this. So we get that it's theta to the power of, why did I have here minus? I don't know where the minus came from. It's not there. Theta to the power of alpha plus sum xi minus 1, e to the minus beta plus n times theta. I'm sorry?
We're not even mentioning that the xi's are independent.
Okay, so this is an example for the case where we have an IID sample.
It's just always going to be that way?
Unless we, we will usually, if we get an exercise, we'll mention that specifically. It should be clear from the context. But usually we will consider IID samples. Okay? We talked about a few cases where the samples are not IID, but in general that will be the case. Okay, I didn't write it down, but I did mention that. Okay, so what is this? This is an unnormalized distribution, right? Because we ignored all of the constants in the way. But what kind of distribution is that? Well, you know the answer already. What's that? You know the answer, right? But what are the parameters? So let's say alpha prime is the parameter of the posterior. So what is alpha prime? Okay, so we just compare. Great. It's alpha plus the sum of xi. So again, the update here is additive, right? You're just adding your samples to the parameter alpha. And what is beta? Beta plus n, right? Beta behaves like the counter, beta prime, I'm sorry. Okay, of the posterior. Okay, and Let me put this aside for a minute. Okay? So now I'm putting this aside so we can use this table here, and you can use these properties here and tell me what is the L2 estimator in this case.
Well, it's written there somewhere. It's the L2 is alpha divided by beta.
It's alpha divided by beta is the expected value according to the prior. Alpha prime divided by beta prime, right?
Yeah.
Everyone sees that? Okay, so the L2 estimator is the expected value according to the posterior distribution. Okay, and so we need to take the expected value according to this gamma distribution. Okay, so this tells us that the posterior f theta given xn is gamma with alpha prime and beta prime, where this is alpha prime and this is beta prime. Okay, so the L2 estimator is the expected value according to this posterior, which is alpha prime divided by beta prime, which is alpha plus sum of xi divided by beta plus n. Okay, this is really cool, right? Why? Okay, let me write this just exactly the same as beta times alpha divided by beta. Right, it's exactly the same. It's multiplied and divided by beta. What that? Okay, so this I can't move. So I'm writing this again. Okay, no problem. So the L2 estimator is beta times alpha divided by beta plus sum xi divided by beta plus n. Okay? And why did I write it this way? Okay, so how can you make sense of this estimator? What are the dummy samples? The prior is alpha and beta, yeah. So? I can't hear you, I'm sorry. Right, so we added how many dummy samples? Beta, even though beta is not necessarily an integer. Of course, what do you have that? Alpha and beta are positive. Okay, and we assumed even that alpha is greater than 1. Okay, so we added beta samples, where the value of each sample is the mean according to the prior. Right, which is alpha over beta, which is really cool, right? So you can think of beta as the strength of the prior, right? If we take beta to be very large, then we need more samples, and needs to be larger in order to forget the prior and be concentrated on the new evidence, right? To trust more the new data. Okay. What is the map estimator? The mode, according to the posterior, which is
Alpha prime minus 1 divided by beta.
great, which is alpha prime minus 1 divided by beta prime. Okay? Which is, let me write it in the same form as I did here, which is beta times alpha minus 1 for beta plus sum xi divided by beta plus n. So how does this estimator behave? Almost, but we added here beta dummy sample. But here we added beta dummy samples where the value is the mode of the prior and not the expectation. Okay? So these are some sanity checks that you should do. Okay? Try to, if you get a new problem and you find an estimator, even in the maximum likelihood approach and it's Bayesian approach, try to ask yourself, does it make sense? Okay? How does this estimator behave? Does it, okay? So if in the maximum likelihood approach you don't expect to get any dummy samples because you don't have prior, you don't have this inductive bias. In the Bayesian approach you do expect to get some bias, okay? and this bias should make sense in some way, should get it from the prior, as we see here, right? But you also expect that what should happen as n goes to infinity? It should go away. Well, that's a good property, and the Bayesian estimators are under general assumptions are consistent. Okay? So in general, you should check that when you take n to infinity, the effect of the prior decays. Okay? The prior becomes negligible, and you'll get that in all cases, right? All these estimators will be approximately the empirical mean, okay, which converges in probability to the group parameter theta. Yeah.
So taking the prior to be from a conjugate distribution, the posterior would be a beneficial. I think you mentioned it, but this should be our strategy when picking dummy samples.
Not when picking dummy samples. Dummy samples is the outcome. You're not picking them. But yeah, if you need to, if you have some prior knowledge, okay. So this is also a convenient way to express your prior knowledge, right? So if you know something about the expected value, and then you just select alpha to reflect this expected value, and how much you're sure about this prior, you can express that with this choice of beta for the prior, for example. Okay? Or for instance, in the normal distribution, okay, if you have some prior knowledge, as the example I gave during the break, suppose that you want to estimate the average height of people in the population. Okay? You have some prior knowledge about the expected value of this, prior knowledge about the average, then you can set a prior, a normal prior with this expected value, and as you get more samples, you update the prior. You update your estimate. Okay? So also here the updates are additive. Okay, which is nice. Okay, any guess what would be the maximum likelihood estimator? For the Poisson, so no priors? Just guess. Okay, so what is the expected value? What is in the Poisson distribution? What is the expected value of x given theta in the Poisson distribution? It's okay. The expected value of x according to this distribution, it's just theta. Okay. So what would you guess? Theta. No. What would be the maximum likelihood estimator? Estimator. It's only a function of the sample, not of the true parameter. If you don't see theta, just see observations that come from distribution that theta is the expected value of this distribution. So what do you expect? Exactly, the empirical mean, right? So and it's also hiding here, the empirical mean, right? And you'll show that in the exercise. Okay, so in the exercise you'll show that indeed for the Poisson distribution, the maximum likelihood estimator is the empirical mean. Okay, so the dummy samples, you can also compare that to the maximum likelihood estimator. Yes.
Are there sufficient conditions for a distribution to have a conjugate prior?
That's a great question. Did you talk about exponential families? Okay, so exponential families, there is a constructive way to build conjugate priors. Actually, exponential families conjugate itself. Maybe I'll have a question in the exercise, but that's a good question. But it's not. It's a sufficient condition. So there are also distributions which are not exponential that do have conjugate priors.
Is there a constructive way to find them? Or?
Not for exponential families, I don't know of a constructive way, but actually most of the distributions that we're considering are exponential. Actually, hard to find almost all. I think almost all of the distributions that you saw are so far in the course are exponential. Okay. There are a few exceptions that are actually useful, but okay. Any questions so far? Great. So the conjugate prior was a method for it is mathematical convenience that we had for finding Bayesian estimators. Okay, but there is one Bayesian estimator for which we don't really need the posterior distribution. Which one is that? It's written there. No. The maximum posterior. Okay, the R1. Okay, and actually, I think you talked about in class that it's actually the map and the maximum likelihood estimator share some common properties. Okay, so let's talk about that now. So can I erase this part? Yeah. What is in this case? The example that we just saw, we just showed the conjugate power. Yeah, so what we showed here is we took the Poisson distribution for x given theta. We took a prior over theta to be the gamma distribution, and we showed that the posterior is also gamma, but with updated parameters. So in this case, we say that the gamma distribution is conjugate to the Poisson, or it's a conjugate prior for the Poisson distribution. Okay? Actually, you can also show that any guess for the exponential family, exponential distribution, I'm sorry, what would be the conjugate prior? Yes. Why do you say that?
Because exponential is related to Poisson.
Okay. Not
And Poisson.
the gamma distribution is not a conjugate to all exponential distributions.
No, but it's like Poisson and exponential are
Okay.
inversely related.
Okay, that's a good intuition. Also, we saw in the last Tirgul, which was 2 weeks ago, an example where we found, I think, the L2 estimator for the exponential distribution, and we saw that the posterior was gamma. So actually, you can show that more generally, the gamma distribution is also conjugate to the exponential distribution, not exponential family. Okay, can I erase this? Great. So what we'll do next, we'll see first of all how to find the map estimator without going through the posterior, which sometimes is more difficult than just maximizing this term. Okay, and we'll also compare this to the maximum likelihood estimator to see how they're similar and how they're not similar. Okay, so let's talk about the map versus the MLE. Okay, so first of all, let's see how to find the map estimator without going through the posterior. Okay, so just let's write it again. The map estimator is the arg max of theta of the posterior distribution, right? And again, okay, this is just proportional, right, to the arg. Okay, so since this is proportional to f of x and the likelihood times the prior, okay, it doesn't change the maximum. We can ignore the normalization factor. Okay? And also, we can take the log. Okay, so first of all, you see that this here is the likelihood function, and this here is the prior. Okay, so you already can see that the map estimator it tries to maximize this term that also depends on the likelihood function. And let's take the log, and then we get that it's equal to the arg max of the theta of log of x n. Okay, and since we're taking the log of a probability of an IID sample, which is what we assume here, so it's simply the sum of logs plus log of f of theta, of the prior. So we get some trade-off here, right, between the evidence, the data that we get, and the prior. Okay, and what happens as n goes to infinity? Okay, so this term remains constant, right? But this term, okay, becomes more and more dominates the whole function, right? And as n goes to infinity, we get that finding the max estimator is approximately maximizing this term, which is just as maximizing the likelihood function. Right? You saw this in class, right? Okay? So asymptotically, the MAP estimator and the ML estimator, which is, let's write it again, the ML estimator is the argmax over theta of sum I goes from 1 to n of log f of xi given theta. Okay? So asymptotically they're equivalent. Okay? When else would they be exactly the same? Under what condition? Right. If you have a uniform prior, which does not always exist for a continuous variable, but if we have a uniform prior, then they're also equivalent. Okay? And this also shows us not only the relationship between them, but it also shows us that to find the MAP estimator, we don't really need to find the posterior. Okay? We can just differentiate, right? We have this function, which is a function of the prior and the likelihood. We can just find the maximum of it. Just differentiate this with respect to theta and find the maximum. Okay? Equate to 0 and make sure that it is indeed a maximum.
If not equal priors, then it won't matter.
If what?
If
Right. If the prior is not uniform, you're absolutely right. They're different, they're only asymptotically. Either way, we don't have to find the posterior. We just need to, because we just need to maximize this function. And this function is not a function of the posterior, it's a function of the prior and the likelihood. Okay? So let's see an example. Okay, let's take the exponential distribution. So let's assume that f of x given theta is theta e to the minus theta x, which is exponential distribution with parameter theta. So let's assume a prior f of theta, which is e to the minus theta, which is also exponential distribution with parameter 1. Okay, or hyperparameter 1. Okay, so the expected value of theta is 1. Okay, and the expected value of x given theta is 1 over theta. Great. Okay, this is 1 here because the parameter is 1. Okay, so let's start with finding the maximum likelihood estimator. Okay, so theta hat ml is the arg max over theta of sum I goes from 1 to n of log fi fxi given theta. Okay, so what is log fxi given theta? It's log theta minus theta xi. Okay? Which is exactly the arg max over theta of n times log theta minus theta sum xi. Okay, so let's call this L of theta, and to find the maximum, we will differentiate it, equate to 0, and then make sure that it's indeed a maximum. Okay? It's important to make sure. So the derivative of L theta with respect to theta is from this term we get n over theta, right? And from this term we get minus sum xi, and we need to require that this equals 0. Okay? And we get that the ML estimator is 1 over n sum xi. Okay? And make sure at home, okay, so we need to make sure that this is indeed the maximum, right? So the second derivative, okay, is what? Is minus n over theta squared, which is always negative. Okay, and therefore it's a maximum. Okay, you need to make sure. So, what does this make sense?
It really looks like the average.
Because the expected value of x given theta is 1 over theta, so we got 1 over the empirical mean, which makes sense, right? Makes sense, but it comes with some cost. Right? What is this an unbiased estimator? So in general, this estimator actually is biased. Okay, so in general, the expected value of 1 over x, okay, is greater or equal than 1 over the expected value of x. So in general, we will get a positive bias. Okay, this is just comes from Jensen's inequality. Of course, this is for a positive x. Okay, so this follows from Jensen's inequality or convexity, whatever you want. But in general, this estimator, this means that the estimator is biased. Okay, so this is an example where the maximum likelihood estimator can be biased, as opposed to the previous example that we saw so far. Let's. What is exactly the same? This is not exactly the same.
We have 1 divided by the average.
Right. So you can write this here. Okay, or if you prefer, exactly the same. Okay, taking the expectation before you take 1 over the value, or okay, actually it's not the same. Okay, the expectation is linear, but this is not a linear function, 1 over x. Okay, this is true for positive x.
So the estimator is going to be biased to be less.
So in general, this means that the bias will be positive, because this is unbiased. Okay, this equals 1 over theta. Okay, think about it and come to me after the class if you're not sure. Alright, let's find the map estimator for this example. And since we already found the MLE, it will be easy, right? We only need to add the prior. Okay, so the map estimator is the arg max over theta. Okay, now we have this term, okay, which comes from here, plus log of the prior. Okay, so we have L theta minus theta. Okay, and now if we differentiate this equate to 0, we just get minus 1 added to the derivative, and we get that the map estimator is 1 over n sum xi plus 1. And why does this make sense? Because we have here another dummy sample from the prior, which is the expected value of theta according to the prior.
But you don't divide by n plus 1.
Yeah, that's strange, but no. Right. So it's like instead of adding a dummy sample, just spreading it over all the samples. Right, so we have a fraction of the expected value to all samples. All right. Any questions so far? Okay. So the last part, I would like to talk about some limitations of the maximum likelihood estimator. So in general, maximum likelihood estimation is probably the most popular approach, especially in machine learning. It's very useful, very practical. However, it has some, few limitations. Most of them are technical, okay, which is good to know, good to be aware of. So the first one we saw is that the maximum likelihood can be biased, okay? And I'm not sure if I'll have time to go over all 3 limitations, but let's start with the bias and find and show another example where we have another important example for an estimator that is biased, and we can actually find a bias. Okay? Even here, actually, it's not hard to find a bias in this case, but I want to show it on a different example. Okay? So, let's talk about the bias of the MLE. Okay? Let's take now, and this is a really important example, so this is why I'm doing it again. Let's take now the case where x, let's write it differently. Where theta now is, we have two parameters for the distribution. Okay, so theta now is vectorial. Okay, theta, let's call it mu and sigma square, the two parameters of the normal distribution. Okay, and let's assume that f of x given theta is normal with mu and sigma squared. So now both the expected mu and sigma are unknown parameters, and we're trying to estimate them both. Or we're trying to estimate theta. Okay, so theta hat ml is mu hat ml and sigma hat square ml. Okay, so the likelihood function in this case, okay, so L of theta is actually a function of two parameters. So in order to find the maximum, okay, we need to find the maximum with respect to these two variables. Okay, so here I will show only the first order condition, namely we'll find a point where the gradient of the likelihood is 0. Okay, and at home you should verify that this is indeed a maximum. Okay, so you need to at home you should take the second derivative and make sure that it's indeed negative. Okay, so what is the likelihood function in this case? So as we had before, let's consider the log likelihood. Okay, which is easier for us. So this is the sum over I goes from 1 to n. Or actually, I defined L theta to be the log, right? So let's call this simply L theta. So it's already the log. Okay, so log of the normal distribution, okay, which is minus half xi minus mu square divided by sigma square, okay, minus half log 2 pi sigma square. Okay, I already took the log and everything here, the sum, and notice that now this is not a constant, right? This is part of the parameter that we're trying to estimate. Okay, so if we differentiate with, okay, so we need now to differentiate this with respect to mu, we need to differentiate with respect to theta, equate them both to 0, and that will give us the first order condition. Okay, so verify at home that it's exactly the same as we did before, that mu hat ml is what? What is it? It's exactly as we had before, so what would it be? It's the empirical mean, right? Because we're trying to estimate the expected value of the normal distribution, so it's okay. It makes sense, and you can also get it, just differentiate here with respect to mu, and you get that. Because when you differentiate this with respect to mu, then this does not matter, this term. Okay, this is also a constant, and you get exactly what we got before, which is the empirical mean. Okay, so now we need to find the maximum likelihood estimator for sigma. We need to differentiate the likelihood, the log likelihood, okay, dl theta with respect to sigma squared. Okay, and what do we get? So we get sum of I from 1 to n minus, actually plus xi minus mu square plus 2 sigma square, right? And differentiating this, we get minus 2 sigma square, right? or actually let me just take this already outside of the sum. Okay, so this is just n here. So the sum is only for the first part, and we got n times this. Okay, we need to equate this to 0, right? And do the algebra at home. We get that theta hat square ml is 1 over n sum xi minus mu hat ml square. Okay? Why did I substitute here mu hat? Because we need to find a point, right, where the derivative, the gradient is 0. So both derivatives should be 0. Okay? And at home, take the second derivative and make sure that this is indeed a maximum. Okay? Great. Great. This is important. Why does it make sense, this estimator?
This is variance with respect
To the empirical distribution, right? This is like the empirical variance, which really makes sense. Okay. So let's see what is the bias of this estimator. Okay. Actually, we don't really have time for that, so I'll have that in my notes. Okay, it's just algebra, nothing special there. But let me just write the final result. Okay, and you can follow the algebra through my notes, and if you have any questions, don't hesitate to post them in the forum. Okay, so just let's write the final result. So the bias, or it's not really the bias, the expected value of theta hat, sigma hat square ml given theta, given the true mean and variance. Okay, so the bias is this minus the actual value. Okay, you can show that it's n minus 1 over n times sigma squared times the real value, the real variance. Okay, so just notice that it's still consistent. Okay, so as n goes to infinity, this still converges to the true parameter. Okay, and if you have this, now that you know this, can you suggest an unbiased estimator? Okay, so suppose we want an unbiased estimator. Theta hat square unbiased.
decrease this from the estimator.
Exactly. So we can easily correct the bias. Okay, so we can define 1 over n minus 1 sum xi minus mu hat ml, and this would be an unbiased estimator, right? Because this is simply n over n minus 1 and sigma hat square ml. Okay, and the expected value of this is, we know already that it's this, and just cancels out. The bias is cancelled out. However, it's not necessarily. It's n minus 1. Okay? So it's not necessarily better to have an unbiased estimator, right? It's not necessarily, or in other words, it's not necessarily a limitation to have a bias. Why is that? That's the final note for this class. Exactly, because we have a trade-off between the bias and variance. And in this case, we won't show it today or in the course probably, but in this case, it's possible to show that the maximum likelihood estimator, in this case, it has a better MSE. So even though it's biased, it has lower variance with respect to this estimator, and therefore, it's better in terms of the MSE. Okay, that's it. Any questions?
the definition of code. Yeah, I also, like, Jesus said just yesterday, like, it rings a bell, and that's how I understood it. And, like, when she wrote this, like, when she made it, there's something. So I just, like, when I understand stuff, it's like, oh my god, this is so confusing.